excited to be here today. KubeCon is a dear conference, which I always go back and watch all the great sessions and read all the great content in InfoQ. So I'm very happy to be here to share a little bit from what I've learned and what we've learned from our customers' journeys as well. So streaming all the things, patterns of effective data stream processing, and what does it even mean? In this session, I'm going to cover some of the patterns. I'm not going to go deep dive into exactly how you configure each one of the things, because this is oftentimes very specific use case that requires specific understanding of what it is that you're physically building, what's the business that you're serving. But I am going to give you a overview of all the streaming patterns that takes place and where usually people makes mistakes just because it requires so much details and so much attention. And sometimes things can get confusing, especially when we're balancing multiple data infrastructure for multiple parts in the organization. So, as you know, data is everywhere. Yes, data streaming exists. There's also a system that does batch, right? There's a huge part of analytics in different organizations, either if you're using a data warehouse or if you're using things to process your own data like Apache Spark or things like that. But batch exist. On the other side of data streaming, there's the side of the applications. We're building microservices applications that also process data. Sometimes we leverage things like Kafka, right? We have applications that do produce events, applications that consume events. Sometimes we'll use Redis, sometimes we'll use other databases in order to maintain our data. So when we think about it, data is everywhere. It's not only the data streaming. And what happens to most of us is when we enter the data streaming world, we are already experienced engineers. Most of the people I met that came into data streaming coming from a background either in batch or in application space. And this is where things get complicated because we are bringing the patterns and the things that we knew before, and we're trying to mimic the similar behavior in the data streaming. Well, it's a great practice as an engineer, as the industry evolves, as our data architecture evolves. Sometimes it's also important to remember to forget things. Now that can be a little bit confusing, right? Because we're doing a lot of work to gain that knowledge, but sometimes we do need to rethink what is the fundamentals, what are the basics that we're targeting, and how we can really build stream processing that is as efficient as possible. So a little about myself. I wrote 2 books for O'Reilly and helped review more than 10 books for O'Reilly related to the data infrastructure. I'm a people manager. I'm very privileged to be able to manage a great team, brilliant team. And in my background, I was a software engineer full-time. I'm coming from the big data world. So I did a lot of batch processing. I did a lot of machine learning at scale. And recently, I joined Confluent almost a year ago, where I entered the streaming, and this is why I'm sharing all my knowledge with you today in order for you to also take the insights. All right, so what are the challenges? There's a huge list of challenges that exist in streaming. Yes, we all, we saw it before. There's the throughput, there's the scalability, there's the latency. It can be millisecond, it can be maybe 5 seconds. But we are going to speak about only specific challenges that I saw people are, oftentimes get confused the most. So the first one is exactly one semantics. Exactly one semantics is part of our different semantics that we're building. We were very good at building exactly one semantic when our infrastructure is constructed of one platform that we need to manage. But we do know that there is an end-to-end platform and there is a connecting tissue between the tools that we're using. And this is where exactly one semantics become even more challenging. We're going to talk about join operations. Join operations in the analytics space. If you're coming from a batch world, if you're coming from a DBA world, it's prevalent, it's everywhere. We're doing a bunch of joins operations. Yes, it takes longer. Yes, it requires dedicated strategies to optimize. And we are bringing them into the stream space. And that means we need to understand how join works when we have endless stream of events that comes in. It's unbounded. We're not looking at specific anymore. We need to be able to do that at the huge scale and the speed that the data comes in. We're going to talk about error handling and recovery. There's some new capabilities coming from the open source, which I think is really exciting. If you're managing a cluster, or if you're a developer using a managed cluster, this is for you. And lastly, we're going to talk about guarding the gates, how we're building quality and security right at the beginning. So these are the patterns that we're going to cover here today. Let's start with exactly once semantics. So exactly once semantics is one of our 3 different event guarantees. We usually discussed exactly once, which means I'm processing a transaction exactly once, at most once. I know I'm processing the transaction at most 1 time, or at least once. I can process it multiple times as long as I'm processing it once. So what happened in the past? In the past, we had something called lambda architectures. Any people here that still or in the past managed lambda architectures? If you want to raise your hands, I see a lot of hands up. Okay. So in the past, we used to manage lambda architectures. And why did we do that? We needed the data, we needed fast information and right-in-time information. So we had the speed layer. But we couldn't trust the data that came out of the speed layer to be 100% accurate. So while we had the speed layer, we constantly ran batch processing, either an hourly or nightly, in order to make sure and compare the true result between the stream processing and the batch processing. So while we were using it, we're still going back and kind of making sure that this thing is still relevant for our data. Now, our technology evolved, and we now know how to do better things than that. And so we moved into Kafka architecture. And Kafka architecture usually is built, there you get Kafka cluster, you ingest data, ingest events, you have some stream processing engine, and you have that exactly once, or you want to have this exactly once between these 2 systems, right? Each one of them knows how to create exactly once for themselves. But how does notion of time works in these systems? If we take a step back, in order to create exactly once, we need to sit on the building blocks of what is the fundamentals of stream processing. And the fundamentals of stream processing are events coming into the system, state of the application, and I'm managing a stateful application, is it a stateless application, where do I live, and what is time? Now, what is time is a really interesting question. I don't know if you ever got a chance to look at logs, to look at events, to see a timestamp, and ask yourself, what does that timestamp represent? What do I know about this timestamp? Okay, it exists, but what is the meaning of that specific timestamp? So usually in the stream world, we'll look into 4 different timestamps that we can leverage. One is the event, right? When does the event occur? One is the storage. When did we actually wrote that event into an existing storage? Third one is ingestion. When did the event got ingested? And lastly is the processing. When did we process that specific event? Now, how we're going to pick between these 4 ways of looking into timestamp is going to determine how our system going to work and our architecture. And I'll give you an example. This is time and calculations. If I'm looking at event time, and if I'm looking at storage time, because my system is distributed, I'm looking at time that is immutable. It never changes. Event time occurred at one specific time. This event will never change. That is what it is. It was written to disk. That's what it is. It was written at a specific time. Versus a mutable system that is not deterministic system that is often harder to debug, harder to create any promises around it. This is when we're using time that comes from ingest. And why is that? It's because anyway, our ingest is a distributed system behind the scenes, right? So ingest could be depending on which partition ingested that specific data. Similar thing with processing. Which one of my node actually processed the data, going to get a different timestamp. So one takeaway is sometimes the system will give you that flexibility to decide which timestamp is going to be the timestamp that you're going to use for your event guarantees. Strong recommendation, use event time or use storage time, probably event time because you don't want to do the travel to a specific storage if you're building that, and work with this. All right, what is event and how do we look at event and when our events are considered late and when our events considered on time? One of the challenges of exactly once consistency is you want to be able to process the event at time, but sometimes events are late. So if we compare event timestamp to the most current watermark, if we see that a timestamp specifically is smaller than the watermark, this is when we're saying that the event is late. You can see the timeline of the events. If the timestamp is bigger than the watermark, this is where we're saying the event is on time. as within the window that we're expecting it to come into the system. So as you're creating this new language for stream processing, please use these references of event is late or event is on time. This is another example of how to see the different event timestamp. And sometimes bad things happens to good timestamp. Because what happens, we get late events as we can see there in the bottom. And we know we have to still exactly one process them. Now, how do we do it when we have the notions of windows, right? When we have the notions of windows, usually these would be time-driven or event-driven. We'll talk about it in a second. They will allow some lateness for late arriving events, right? Especially if we have exactly ones. And it's going to be dependent by the type of window that we're processing. So here we're going to dive a little bit deeper. Specifically, I'm going to use reference from the world of Flink, Apache Flink, if you heard about it, just because it's going to make it a little bit easier for us to understand. So one notion of events is a tumbling window. A tumbling window is I have the exact timestamp of where I'm reading. I'm reading 1 second, and all the events that are going to come inside this 1 second are going to be the one that I'm processing. And then it moves really nicely along the way. The second one is sliding window. Now, sliding window, it's a little bit more complicated because although it has kind of like a fixed amount of time where it lives, it still moves, but it moves either 1 event or 2 events, depending on how 1 second or 2 seconds, depending on how we're defining it in the beginning. So this is great if you're doing events from GPS, geolocation, or anything like that you want to calculate the specific amount of device, for example, that exists in a specific place and process it, just as an example. And the last one is considered the more advanced one, but often being used in systems where we see peak of information coming in and out of the system. That's a session windows. A session windows will take all the events that it sees within a time range, which means there's a TTL. If it didn't get any events here, for example, up until half a second, it will close the windows. Once it starts getting more events, it passed that idle time, it will open another window, which means it's willing to wait that idle time before it's going to start processing and opening another window again. This is great when we have peaks in our event where we're serving users. We know it's specific time. We want to have the cluster always up, but we also don't want to keep a window open forever, or we don't want to process windows that gives us at the end empty results, because that usually downstream will turn into null values that's going to harm our processing as well. So if you are dealing with something like that, session windows can really help. So how do we put all these systems together, right? Each one of our systems today, if I'm looking at Apache Kafka or if we're looking at Apache Flink, each one of them has exactly one guarantees by themselves. But we know that the connecting tissue, usually in between, is where things can get messy. So here, for example, I have a data source that reads from Kafka. It can be any data connector that I'm building. Flink takes that information. There's some window aggregations taking place. And then data syncs back into Kafka, and later on some applications read through it. But in reality, because both of the systems are distributed systems, there's going to be multiple things happening at one time. And this is where things becomes even more challenging because you want to be able to manage that and control it. So, well, the scope of each one of them is going to work well, and Flink specifically used checkpoint mechanism under the hood. Kafka has different guarantees with the protocol. We need to be able to kind of close the loop of that exactly once across the system. So this is one challenge where I see some of the people get confused a little bit building their own system, but there is a protocol that already exists that I would love for you all to know about it, and if it's something that could be relevant to you, please use it because it's already built in. And that's the exactly once two-phase commit. So how exactly once two-phase commit works? If I have my Kafka cluster, Kafka on its own has exactly once. I'm configuring it to do exactly once, and it's all good. Then the Flink job manager, what it's going to do is going to inject checkpoints barrier. What it means, it's going to write a file with dedicated magic bytes in the beginning that tells it that this is going to be the beginning of the two-phase commit transaction. It's going to take that information after the data source got in and start processing, and it's going to save a snapshot offset into the state backend. The reason that it does it is because Flink under the hood for exactly once leveraged the checkpoint mechanism. If there's any failure happening in the stream processing, it's going to go back and pull that information, so we're guaranteeing that exactly once. So here's where we're connecting Kafka to Flink at the beginning of the ingestion. What we do from the data source is we're passing that file, we're passing the responsibilities of the checkpoint barriers to the actual window processing. And this is where we're connecting back to the windows that we just talked about before. After the windows again snapshot against the state backend, and it passes the checkpoints barrier to the data sink later on, for example here, to our Kafka. After the data sync, all the information is sending pre-commit transaction back to my Kafka cluster. And in order to close the loop, my job manager is going to do a check-in on each one of the parts that are part of this transaction to make sure ask them if a checkpoint is complete or not. If Kafka has finished, it's exactly one as well, and the other side is going to commit the external transaction back. And this is how, essentially, we're closing the loop while we have Flink that manages the protocol for us, and we're implementing it across. Now, this implementation exists for Kafka. There's an interface in Flink if you're using something else. There's other implementations out there, but if you're using something else and you do want to implement, there's a list of 4 or 5 functions that you will need to implement for each one of the steps that I just discussed. And essentially what it means is checking that you have all the information and writing the special files that Flink needs in order to give us these guarantees. So if we sum it all up, we know we have the pre-commit, right? That issues a commit in the beginning. We have, if any one of the pre-commit fails, rolling back, doing abort, leveraging the checkpoints mechanism. And after everything succeeds, then we know for sure, we guaranteed that it's completely succeed with exactly once. So this is how everything connects back to our system. And this is how we're doing exactly once across different systems. So this is one of the patterns. The second pattern is going to be join operations. This is, again, another pattern depending on which space we're coming from. We're coming from a more of a DBA world. We're coming from a more distributed batch processing world. But this is definitely going to impact the way we're mentally thinking about stream processing. So there's 2 notions of join operations in a stream. One is considered slightly simpler or more easier to build for, and the other one is considered a little bit more complicated. So the first one is stream batch. Let's assume I have a table of information and I have a stream, and I need to do a join operations between that stream and the table. It's very easy for me if I save the table in some state that it's fast to access, and so I can do the join, and there's no problem at all when I'm processing that data, because my table is static. So this is a happy scenario. All you need to do when you build that is thinking how big is the table? Do you need to do a lookup to the table, or can you save it somewhere? Can you spread it across the nodes? Can you save it somewhere that has fast access? And that's about it. It's very similar if you're coming from the analytics, the batch processing space, it's very similar to that. The second one is the more challenging one, because here we have 2 streams. Each one comes into the system. We want to do some join operations on top of them based on some mutual information that they share, either a timestamp or some content of that information. And here sometimes we're saying, hey, I want to do exactly once, right? I want to make sure I'm joining all the events exactly once and I'm processing this stream. And this is where things become really complicated, because here's when we're trying to build different solutions in order to make it happen. One of the things, it's a pattern, I really like to call it Puppy's Shelter. This is a shelter for events that never found their friends. For example, you can see here, In the views, there's event D, there's event E, but there's no join result at the end. And so both D and E are gonna go to the puppy shelter. And we wanna make sure these events are being adopted because we're doing exactly once. So what happens is we go back and we're trying to build more data pipelines, more data flow, try and ingest them again with different timestamps, doing all this back operations. And while all of these works, if we have to, maybe we can find a different solution and put it in some queue that we can process them separately. So we can take care of these puppies, but also don't overload the systems with things that are usually unnecessary just to solve a very specific end case, because this is where stream becomes even more complicated. So if you're dealing with this thing, think about this cute little guy here and how you want to treat it, but make sure that you are not overcomplicating a system that sometimes can be already complicated. And you can see here how, you know, all of the other events kind of found their friends. Even B, it's kind of like at the end, it's going to get here because at the end, it did arrive. All right, let's talk about guarding the gates, discussing data integrity, data quality, and some of the challenges that we have there. So what is data integrity and how does that relate it to data streaming, right? Like it's kind of like a common topic that we talk about in the data world, so how things connect. Data integrity for data streaming means it could be a physical integrity. Oftentimes we can check things, you know, if it's really the data that's supposed to be there. This is usually the work of a data science later on. There's a logical integrity that we can do. We can check the types, we can check the range, things like that. And there's also something called referential integrity that checks relationships between different tables. So you won't get to these lost puppies, but at the end, something that we need to consider. So this is where data cleaning and data validations is the real words that we need to use. If anyone tells you data integrity, go look in these things. So these are the things that we need to take care of. We need to take care of there's no null data. We need to take care of there's no bad types in our data. And we need to make sure it's part of our architectures when we're doing streaming. So any applications or any downstream processing is already leveraging what exists there. So if I'll go for a second back to Kafka, as everyone knows how Kafka looks from an architecture, raise your hand if you saw this before. I see a lot of people nods their hand. Okay, perfect, thank you. Producer, Kafka brokers at the middle, consumers. At the bottom, I have some Flink applications. But what we can do is on the connecting tissue between the producer and the consumer, right over here is where we can make sure that the data that flows over the system actually gets there at the right quality. So what are the things that we can do today if we already have a Kafka cluster? We can do schema validation. We can do schema evolution. We can do input validation, really critical, type, format, range. We can do, there's also generic things that we can do, but this gives you kind of like a high level understanding of the things. There is one tool that exists for it, but you can build your own. Schema registries is the tool where you can manage the schema, throughout the data serialization process. It also helps you manage versioning. Sometimes for some people, versioning is critical for the schema, especially because we know the data that comes into our system from upstream sometimes change the versions all the time, and we need to be able to capture these changes and address them. And we need to be able to validate that this is the right schema or block the data. So this is another pattern that data streaming really needs to mature, in my opinion. And then we need to take care of that interoperability. But how does it look like in the architecture itself? So if I have a Kafka producer, right, and a Kafka consumer at different sides, and I'm connecting what I call the governor, someone who is going to govern around the rules and going to help me make decisions, I can give it the schema and I can give it the rules that I want to enforce on top of this architecture. So when my producer produces, it gets the schema. When my consumer consume, it gets the schema. It also gets the rules that it has to comply. So my data now has to comply. So what happens here in the stream is instead of me building more and more applications to validate the data or only validating it downstream after I have multiple data streaming pipeline pushing data, I can push all these operations to this. So already here, I'm stopping what needs to be stopped. And that's really useful because what happens to us in organization is usually we build thousands of pipelines and thousands of consumers are going to consume our data, and we want to make sure it's in healthy shape. So how does it look like? This is a JSON file, all right? So I have my schema, I have my rule set, and I'm giving it some name, check device temperature, some IoT devices. The kind here is conditional, which means I'm going to give it a condition that it needs to follow. CEL, it's common expression language, something that Google created some years back. And then I'm giving it the expression. For example, message name shouldn't be null. And what happens on failures, send it to a deal queue. So here I'm already creating another applications that I need to manage and maintain by creating this JSON file with the dedicated rule set. Now, which deal queue topic, send it to some bad device 13 that later on I can go back and check these events and fix them as necessary, or roll them back, or decide what I want to, or just dump them if I wish to. Another thing that happens to us is because the upstream data that comes in, especially in the stream processing, always change the schema. And that sometimes breaks our system downstream because we're very much dependent on the schema that comes in. So we need to be able to make some conscious decision here. We're either blocking it and saying we're not accepting this evolution, or we're accepting it and we're making the necessary changes, triggering the necessary alerts, and so on. So how do we do it? Similar thing, we have a JSON file. Here, this kind changes. It's not conditional anymore, it's transform. Transform, what type? CEL field. So for example, my expression here, if my name is full name and value is null, then construct this value from here, which means I'm allowing this transformation to happen to my schema, and I'm already filling it out with some value, right? So this is kind of like very simple to short if in Java. Otherwise, take the value. And that helps me again, not create more and more applications to manage that downstream. I'm already pushing it and loading it on top of my existing infrastructure. So if I'm putting it together, I have my Kafka ingesting data, making sure I have this exactly once guarantees, and then I have these quality rules and governance rules that help me manage the interactions between the different systems. Right, so we talked about guarding the gates, and I have one more thing that I want to say around the challenges that we have before I'll say a couple of words about AI, and this is about errors that happens in our system. So when we are building streaming systems, one of the biggest challenges that we have is failures and knowing where the failure originated. At the end of the day, we're going to get multiple logs, we're going to get some job server that's going to give us some information. And now I realize it's small, so I'll walk you through it. But essentially what happens, Flip, is because Flink is part of the Apache Foundation, Flip is essentially the Jira ticket that we're implementing in the open source. And then there's a new Jira ticket that currently we're working on. It's going to be released in the next couple of weeks, maybe after the holidays. But this is pluggable failure enrichers. And why that's critical for data streaming is because we want to be able to automate some processing around this failure to either mitigate the failure in real time or know who is the right person to wake up at night, or build some process that are more healthier around this stream processing. And what you see here is additional of labels. This is an interface. When we are creating exception in our applications, we can be conscious and say, this is a user problem or this is an admin problem, which gives me a lot of power to decide what to do next with this exception. Things like user pattern can be any arithmetic expression, something in my app specifically. Things that are more admin problem is, heartbeat, I don't get access to the data that I need, or something happened, disaster, I don't get any access, nothing works in the system. This is something that an admin can probably solve versus a user when we have some arithmetic failure, for example. So this is another best practices when we're building stream processing, is to make sure as we're building these applications, we want to make our lives easier, hopefully, by being deliberate in giving the labels of what a failure here could be and what would that mean. Lastly, because sometimes our data infrastructure will need to support something like AI or data processing for AI, or data modalities where we need to now not only support structured data, but we need to also support unstructured data and things like that. I always have this, what I think is kind of like a funny meme. I don't know if you feel similar to it. Yes, sometimes we bring AI into places where we don't need it, but if we're building data architecture, we should be ready. And by the way, if you don't know, AI jobs are on the rise, and there's a very interesting connection between AI and data streaming applications that I've seen across our customers. Things like fraud detection with all the banks and security organizations, recommendation system. We want to be able to recommend product or recommend, a next show that you should watch in real time. Dynamic personalization usually goes together with recommendation. Predictive maintenance, if anything going to happen, we want to be able to predict it. IoT-driven insights. I'm at a mining company that actually they don't do crypto mining, they actually do physical mining. And IoT-driven insights, it's critical for them because everything that happens in the mines, there's no people monitoring. Everything there is robots and everything there is IoT. So sensors that send signals. And the insights from there is critical for them to get it in real time, because if anything happens with the carts in the mining, every minute could cost them millions of dollars. So it's really critical for them. Supply chain or any real-time optimization that happens. So where real-time comes into place and how our architecture changes as we go. We have data ingestion. Oftentimes, this already exists. Sometimes our schema is going to change. What we do need for machine learning is we need to make sure that data validation is in the right format, the right size, and something that our system can process. So going back, if there's something I can overload onto my Kafka cluster, it's going to save me a lot of time and a lot of efforts in that space. And also if the schema changes, if I can control it and decide that this event is getting blocked early on, it's going to be better for me. On the processing layer, it's probably a similar approach of the state management. Sometimes we will need access to dedicated hardware to process some of the requests. We will need sometimes here dedicated storage. Sometimes, especially with Gen AI and LLMs, there is a notion of short memory and long memory. Short memory is what I got right now from the user. It should be very fast to access memory because I want to maintain the context. Long memory means that there's a longer conversation, things that I'm learning about my user from my interaction, and every once in a while I want to load it back, but I don't necessarily need it accessible all the time. So this is where the processing layer together with the storage becomes really interesting, where you have different type of storage. You can imagine hot storage, and later on cold storage or mid-tier storage. And all the retry recovery logic checkpointing becomes really critical. Here, for example, with Flink, right? Flink is stateful, has a state management, what we call kind of like a built-in storage that it can tap into, which could become my short circuit knowledge if I need that. And lastly, the AI integration, the model itself. Sometimes what we'll do is we'll serve the model through REST API, and we want to be able to connect it to the rest of the system. So we want to build an application where we get our input from the user, we're sending it to some model, maybe we're enriching it with existing data. This is sometimes what we call RAG pattern, retrieval augmented generation. We're enriching the data, so later on when we're sending it back to the model has the context and the information it needs to give us an answer that hallucinates less. And that's usually going to be part of my stream processing pattern, just because this is where I'm combining my batch and stream oftentimes of the information. So here I can connect through REST API and have my processing layer, for example, Flink. Flink has Flink AI capabilities where I can register my model together with Flink through a REST API. So I'm going to give it the URI, I'm going to give it the credentials that it needs in order to connect and kind of make it happen for me and call that existing applications that enables that. And under the hood, similar thing that always we have in the data space, we need to be able to monitor, we need to be able to observe. One thing that happen in machine learning is feedback loop. Feedback loop helps me fine-tune my model. This is something that I want to be able to do as close to real time as possible if I can. And usually here there will be a separate data pipeline that tracks the actual response from the user. If the user is happy or not, sometimes you see things like thumbs up, thumbs down, or if we're doing predictive, like we're predicting what's going to be the actual time of one of my rides, for example. It took 15 minutes, but we predicted it's going to be 10 minutes. There's going to be a feedback loop that continuously feeds my algorithm back so we can fine-tune and improve that. And it's going to be a separate pipeline. It's going to be part of the monitoring and observability of my machine learning system. All right, so what are the things that we talked about was kind of like an overview of all the different problems that you can imagine in the data streaming and touching on a little bit of what's coming down the stream, down the road for machine learning as well. So we talked about data quality and deal queue and kind of putting that governance where we need in order to eliminate challenges downstream as much as possible. We talked about exactly once, end-to-end. We talked about why join is hard and why the puppy shelter, think always about the puppy shelter, what the events is going to be either out of order or sometimes not find a friend somewhere. What do you do when you are coding that join in your Flink application? Make a conscious decision about that early on. Speak with your product manager, make sure they're on board. How to deal with healthy errors so we can all work together as a team, the infrastructure and the application developers. And yeah, we already talked about joint operations that require strict planning. Yeah, that was for me. Love to connect LinkedIn or Blue Sky or whatever favorite applications you like. Thank you.
I think we've got about 10 minutes if people have questions. Way in the back. Do we have a microphone in the back? Or am I just going to start running?
Hey, so I had a question about, so in the streaming system, if we want to do AI integration, you said we can do like a REST API call, right?
Yeah.
So that slows down the processing because like in some of our use cases, we have like integrated with AI models and we see a lot of latency because the model can take time and our stream can have like a lot of back pressure. So is there any capability in this system which can be leveraged to, fasten that? Or like, speed the processing?
Yes, because we're connecting kind of a stream processing with either probably a REST API or some microservice that lives somewhere, there's a question about rate limiting, how many requests can I send this server, and also what's the size of the request, what's the size of the context. Sometimes we need to go, depending on the machine learning that we're building, we have to go through embedding process. That embedding process can take longer than we anticipate. And so it's a little bit about our stream processing works really well, but then we're adding this new capability that needs to be able to operate at the same speed as we wish. And then the question is, where do I get my models from? Are my models internal? It's something that I deployed locally. I took one of the open source models that exist today in the industry. I was able to fine tune it and get it to the level that I need. And then I'm hosting it very closely to my stream processing. And then it's a question of time travel, right? What's the request and what's the size? Or am I using existing models like OpenAI or Claude or Gemini or things like that? This is where I'm essentially dependent on somewhere else. So some of the solutions that I've seen that people are building, and that's again very a use case decision to make, is building caching in your application. So if you have some information about this customer, some response that you can give them back to kind of help them wait a little bit longer, but they still feel like they're engaged, this is one solution that you can do. You kind of prompt them, hey, we're reaching out. If that's a chat, for example, hey, we're reaching out. Hey, we're checking this. Thank you for, kind of a list of events that can keep them engaged. Or if it's something that is more like predictive, you're going to return a number. For example, maybe you have some caching information about previous or similar calculations that you did in the last couple of minutes, and then you can bring it back from your hot memory instead of sending it to the model. So you have a caching system right in there that validates these reads. I think with the generative AI part, it becomes even more challenging, especially around time and latency, because we have to think smarter about how we give something to the user, knowing that there is a person there anticipating a response, while our package is going and traveling to the model and back. Hope that helps.
Any other questions? Well, I'm sure Audio will be up at the stage if you have anyone you want to ask her directly. Let's give her another round of applause.
Thank you.